It's my great pleasure to introduce Professor Rahul Roy of Indian Statistical Institute, New Delhi. He is a colleague of mine and indirectly a teacher because I was also a student. So he has worked extensively in probability theory, particularly in percolation and random graphs. Professor Roy, he's also interested in the history of mathematics. He is a fellow of the Indian Academy of Sciences, and his alma mater includes Cornell University, where he did his PhD. And he has a book on continuum percolation with Ronald Meester, which is considered a classic in this domain. Today, we are going to have Rahul talk about voter and majority dynamics. So I guess even if we don't understand the probability and stochastic processes, which I'm sure I won't, at least we will understand the political science consequences and implications. So Rahul, thank you for being with us. Welcome to the GamesNet webinar series, and the platform is yours.
Thanks, Digonto, and also Anirban and Malik for asking me to speak here. I hope this goes without any hitch. And the reason why I chose this talk is twofold, because, well, it's a very recent paper, and more importantly, in the GamesNet webpage, I saw I think one of the first talks was on opinion dynamics, and this is on opinion dynamics. And one of the last talks was mean field, on mean field applications in differential games. And this has lots of mean field applications. But I'm approaching it as a mathematician, a mathematical physicist in some sense. So although the mathematics is completely rigorous, the physics part comes in the mean field. Okay. And as you can see, this is joint work with Arpan Mukhopadhyay, who's at University of Warwick now. And this was part of his thesis. And Ravi Mazumdar, who is a colleague at University of Waterloo. And this is online and Journal of Statistical Physics until it's published when they pull it down, because you have to pay for it. And we don't pay basically just to publish our articles. Okay. So the social literature studies how social agents interacting under very simple rules learn the true utilities of their choices, opinions, or technologies over time. And so the two questions we study here are, can the social agents learn or adopt the better technology or opinion through simple rules of interactions? And if so, how fast? And also, what are the effects of the presence of stubborn agents having fixed opinions on the dynamics of opinion diffusion? Okay, to be, one of the colleagues, one of the people who was a speaker here in your GamesNet series was Kalyan Chatterjee. He, in fact, had talked to me about a model of learning, a very simple model of learning on new technology and everything. And this is more than 10, 15 years ago. And he had an article in this Journal of Applied Probability on it. And then there was one part which was missing. So we had also worked on it. And a few years later, we had published. But I'm not going to talk about that. I'm going to talk about more classical voter and majority rule models. So we are considered a setting where the choices available to each agent are binary. And so we call them just 0 or 1. And we'll call them the opinion of the agents. And the two rules which we'll be following are the voter rule and the majority rule. And I'll explain what they are. Switch off my phone. I'll explain what they are in the next few slides. So in the voter rule, an agent randomly samples one of its neighbors and then decides to update its opinion according to the opinion of the neighbor, this person sampled rather. Okay. And the simple rule basically captures the tendency of an individual to mimic other individuals in the society. And it's called the voter model, but it actually comes from physics, and it's really an interacting particle system. For those of you who know it, it's an interacting particle system But it's called voter rule because there are two choices. And in physics, I mean, the interacting particle system takes two values, the spin up or spin down. So that is the electron in IC models and other things, what they call it. So that's why it's also a binary thing. In the majority rule, instead of sampling a single agent, an updating agent samples 2k neighbors. We purposely keep it even, as you'll see soon. So, and adopts the opinion of the majority of the sample neighbors, including itself. So the total number in some sense is 2k plus 1. So we'll always have a majority. And this rule basically captures the tendency of the individuals or in the society to conform with the majority opinion in their local neighborhoods. Not that it's a good thing to conform to the majority opinion, as we know in our own country nowadays, but still, it happens. Okay. So mathematically, we consider a network of n social agents, and this network is a complete graph. So each agent is a friend or a neighbor of each other. An opinion of any agent is either 0 or 1. And initially, every agent adopts one of the two opinions in an IID fashion. So you just toss a coin and decide whether you're 0 or 1. And each agent considers updating its opinion at points of an independent unit rate Poisson point process associated with itself. So I don't know whether all of you know what is a Poisson point process. So in physics or in mathematical physics or in probability, it's also called a Poisson clock. So what happens is, so you have a Poisson process, a Poisson random variable whose mean is 1. So at the time, so the value the Poisson process takes, at that time, it rings the bell and then moves on. Except that's a continuous time, so there's a continuous time version of it. And what one can say is that if I take two time intervals, one, let's say from S to S plus 1, the other from T to T plus 1, and S and T are different, then the number of times the Poisson clock rings in the interval S to S plus 1 is independent of the number of times it rings in the interval T to T plus 1. And they are IID. So they are the same distribution, but they're independent. So in other words, if I take two disjoint intervals of time, the number of times the Poisson clock rings is independent in these two. Okay. And so at when the Poisson clock rings for the agent, then the agent decides to update its opinion or retain its past opinion. We also give that choice. Retain its past opinion in the sense that an agent is allowed to be biased towards his or her opinion. So what do I mean by bias? So we'll just get there. So an agent with opinion, let's say 0, updates its opinion when the Poisson clock rings for itself with the probability Q0 and retains its opinion with the probability P0. Similarly, an agent with opinion 1. So with probability Pi, you don't change your opinion, whatever your opinion I is. And with probability Qi, you change your opinion when the Poisson clock rings. And we make the agents biased towards an opinion 1. And so we assume that Q0, the probability that you change your opinion is more than Q1, the probability that you don't change your opinion. So that the agent with opinion 1 changes less frequently than an agent with opinion 0. In the voter rule, an updating agent samples agent uniformly at random from n agents from the network and adopts the opinion of the sample agent. Now, I'm saying with replacement here, but we are really looking at what in physics is called the infinite volume limit. In other words, as n goes to infinity, and as n goes to infinity, with or without replacement are really the same. And in the majority rule, an updating agent samples 2K agents uniformly at random with replacement and adopts the opinion of the majority of 2K plus 1 agents, which includes itself. Okay. And also we have the same law. So in the majority rule also, with probability Q0, if you have opinion 0, then you change your opinion. With probability P0, you retain your opinion. Doesn't matter what your sample gives, and vice versa for the opinion 1 also. It's the same thing. So we have this bias inbuilt in both the voter rule and the majority rule. Okay. And the other extension which is there, it's natural, which comes from our paper, is that, okay, we were looking at a complete graph with all n agents are connected to each other. However, we don't need to really do it in both these cases. If an individual, if an agent has a group of size nearly n, in the sense of the order of n, okay, n by 2 or whatever, okay, then that's sufficient. Okay, so we don't really need a complete graph, but the graph should be dense enough. Okay, okay. And in the voter rule, an updating agent samples an agent you know. This idea. So the results, let me just talk about the results. So first, it's just about the voter model. So because there's a bias towards 1 and you're taking n to be finite, the network will always reach a consensus in finite time with probability 1, and the preferred of opinion 1 will be the consensus thing. Okay. So this is in probability, this is referred to as the exit probability of the network. So we also characterize the average time it takes to reach the consensus. Okay. When Q0 equal to Q1 equal to 1, in other words, when it is the case that you always update, there's no bias. So that is the unbiased voter model. And in the unbiased voter model, it is known that the probability with which a consensus is reached on a particular opinion is simply equal to the initial fraction alpha of agents having that opinion. In other words, if the initial distribution of opinions was binomial, let's say n comma alpha, so with the probability alpha you choose 1, and with probability 1 minus alpha you choose 0, then the expected time to reach the consensus is here at 1 for large n is approximately n times h alpha, where h alpha is given by this entropy function for the binomial. So in other words, in the unbiased case, the expected time to reach consensus is of the order of n. For the biased voter model, so let me be now, this is also true for the unbiased voter model. So let xnt be the number of agents with opinion 1 at time t. Okay. So xn0, what I said, is binomial NP. In other words, xn0, each individual, each individual chose it chose 0 or 1 with probability 1 minus alpha or alpha. Okay, so alpha would be the initial proportion of agents with opinion 1. Okay. And this is a Markov process on the state space 0, 1 to n, because xn this counts the number of agents with opinion 1, and there are, so opinion 1 there could be none, which means that we are at consensus, or all n, consensus at 0, or all n, which means we are at consensus at 1. Okay, so these are the so-called absorbing states of this Markov chain. And a continuous time Markov chain is given by this transition rates. So what the transition rates say is that if at time t, there are k many people, k many agents with opinion 1, then the rate it can either go to k plus 1 or k minus 1 or remain at k, because you remember an agent need not always update. You know, it can at the ring of the clock it can just be there. But the remain at k can be just obtained from 1 minus this, or sorry, the negative of these two. So from k to k plus 1, the probability that it goes from k to k plus 1 is okay. So it must, because k counts a number of ones, so that means k to k plus 1, that means it's necessarily the case that a person whose opinion is 0 changed his or her opinion to 1. And how many people are there with opinion 0? It is exactly Q0, sorry, it's exactly n minus k. And the probability that an individual there changes his opinion is Q0, but changes his opinion provided he or she samples from the group which has opinion 1. Because you have to sample and then change your opinion. So the sampling probability is k over 1. N minus k is the size of the group from which the individual is being chosen. And Q0 is a probability that this sample, the person who's changing his opinion does indeed want to change his opinion and has sampled the people with opinion 1. And similarly, you can go from k to k minus 1. That means, again, that it must be a plus and who is changing to 0. Sorry, 1 which is changing to 0. 1 changing to 0, that has a probability Q1. The size of the people who is 1 is k. And and this person must be sampling from the zeros, which has a probability n minus k over n, because n minus k are the agents with opinion 0. Okay. So this is the transition rates, and 1 minus this whole entire thing is the probability that it remains at k. So instead of looking at the continuous time, we can also look at the time when the changes occur. That's called the skeleton of the Markov chain, or the embedded discrete time Markov chain. And I denote it by x tilde n. Okay. And then x tilde n, you can see that is just a one-dimensional random walk from with taking value, which is in this state space here, and 0 and n are the absorbing states. And the jump probability is exactly P, which is Q0 over Q0 plus 1. And that comes from the ratio, sorry, the ratio, oops, I'm going, yeah, that is basically the ratio of this transition over this. As you can see, this n minus k, these will all cancel. It will just be Q0 over Q1. And that is why the Q0 comes, and this is the total thing, which is Q0 plus Q1. So this is the probability of going to the right, and 1 minus this is the probability of going to the left. Okay. And for our purposes, we let R be is Q over P, because this is quite an important thing in our studies. And R bar is the ratio, the 1 over the inverse. So let Tk denote the first hitting time of the state K. That means x and t is bigger than or equal to k from time t. The first time it happened is the time tk. We are interested in the asymptotic behavior of the quantities, the exit probability, where p alpha n means that I am starting with an initial distribution where the fraction of people having opinion 1 is alpha. So then an approximately alpha times n will be the number of people, because it's a random variable, approximately alpha times n will be the number of people with opinion 1. And this says that the probability that, so E alpha is the probability that Tn, so you converge to the opinion 1 before you converge to opinion 0. Because once you converge to opinion 1, you stay. So you don't converge to opinion 0. This is exactly what the exit probability is. And Tn alpha is the probability of being absorbed, of we're getting to a consensus. The consensus can be at 0. That means the entire society has the opinion 0. That is T0. And Tn, which is the entire society has opinion 1. And this Tx and this is just an explanation of what is alpha n, which I told you. So on the event that you start with a fraction, the total number of people holding opinion 1 is x. That's p of x, and similarly the expectation. So our first result characterizes the mean time to reach the consensus state, starting from alpha fraction of agents having opinion 1. So as I told you earlier, this means the initial distribution of opinions were IID Bernoulli, with alpha being the probability of an agent having opinion 1. So what we have is that for all alpha, Tn alpha is theta log n. What this notation means is that I can get two constants, C1 and C2, such that Tn alpha is bigger than C1 log n and less than C2 log n. In other words, Tn grows like log n. Okay, so the above model shows that the mean consensus time in the biased voter model is logarithmic in the network size. And this is completely in contrast to the voter model with unbiased agents, where we saw that, I mentioned that result, that the mean consensus time was n times H alpha, where H alpha was the entropy for the binomial n alpha distribution. So with biased agents, therefore, what we have is that the network reaches consensus exponentially faster than the unbiased case. Okay. So now we look at the proportion. So xn over n, proportion of people which has opinion 1. And because it's also a function of time, we are looking at the entire process as a function of time. So it's xn in bracket should be t. So there's a function of time. Okay. What we show is that if we start off with binomial n alpha, in other words, approximate n alpha proportion of people with opinion 1, then this xn of at any time t converges weakly. In other words, the distribution of xn t converges to that of x as n goes to infinity. However, x is a deterministic process, which initial condition is that initial x of 0, that means at time 0, what is the fraction with opinion 1? That's alpha. And is governed by the following ODE, that the derivative of xt is q0 minus q1. Remember, we had assumed q0 is bigger than q1. This is positive. Xt times 1 minus xt. So xt is a number of people with opinion 1 at time t, not a number, sorry, it's a proportion of people with opinion 1 at time t, and this is the proportion of people with opinion 0 at time t. This is called the mean field equation. Actually, this is called the mean field limit of the system. So as you let n go to infinity, this is the mean field limit of the system. So for large n, Tn alpha, which if you remember was the expected time to reach consensus, so using this mean field limit, we can approximate it by the time the process x dot takes to reach the state 1 minus 1 over n. So, just everybody except one person has opinion 1, starting from alpha. And if we do that, then we'll also, in the second part of the theorem tells that we also verify our first theorem. Verify means that our first theorem is, from the mean field also tells us that the result is Tn alpha goes like log n. That I'll come later. So from the process, we see that xt goes to 1 as t goes to infinity, but that we all know because as the consensus is only at 1. Okay. And if for any epsilon in 0 and 1, if t epsilon alpha denotes the time required by the process to reach that point alpha, sorry, epsilon, starting from alpha, Then we have an explicit relation for a t of epsilon alpha, which is 1 over q0 minus 1, and this logarithmic term, log of epsilon over 1 and minus this. So in particular, when I take epsilon to be 1 minus 1 over n, as I was telling you in my previous slide, that to look at the time taken to reach the state 1 minus 1 over n, then from here, we get that t of 1 minus 1 over n is, so there's a logarithmic in n, and this is a constant, because alpha is a fixed constant. So this is a constant. So what what justifies, I mean, it corroborates our earlier result that Tn alpha is of the order of log n, and then goes to infinity. Okay. However, the process x dot never reaches 1 in a finite time, even though the finite process xn does reach 1 in a finite time. Because when we let the n go to infinity, we're really looking at an infinite volume limit, in which case if there are infinitely many agents, they will never reach 1 in the finite time. It will be an asymptotic one. Asymptotically, it will be 1. But as we said, but Tn alpha is approximated by this, and such approximation of the absorbing time of an absorption time of an absorbing Markov chain is called the mean field limit. Is quite common in the literature. However, except for few cases, there is no real rigorous theory justifying such approximation. So as a mathematician, I should say that we look at this limit and get a differential equation, and we call it the mean field limit, but it does not say that if it is the case that there are infinitely many people, each person with a probability alpha chose opinion 0 or 1, then this should be the true state of nature. It is just called the mean field limit because we cannot do the case when there are infinitely many social agents. Okay. And it's also called the infinite volume limit as a result. But so as I said, it's also worth noting that in the unbiased voter rule, in other words, Q0 equal to Q1 equal to 1, the mean field limit is simply xt equal to alpha. That means for all t. So in infinity, it'll still xt will remain alpha. So in this case, mean field limit doesn't really give us anything. So the mean field consensus time cannot be approximated in this case by the mean field limit. So let me tell you about the results of the majority rule model now with biased agents. So again, it's a Markov chain, and xnt is the number of agents with opinion 1 at time t. And the jump rates now from a state n, that means if small n number of people had opinion 1 to the state n plus 1 or n minus 1 are given like this. N to n plus 1 is, okay, n minus n many people are, okay, here again, a 0 must move to 1. I mean, an individual opinion 0 must move to an opinion 1. How many individuals are there of opinion 0? It's exactly n minus small n. Okay. Q0 is the probability that this individual decides to change opinion or according to what the majority is. And this binomial term says that of the sampled 2k people, there are k plus 1 or more who have opinion this of the n over n, which is the one opinion, and this is the binomial probability that out of 2k with the probability small n over n, that the binomial's random variable gives an outcome which is bigger than k plus 1. So that is the rate of change from n to n plus 1. And the rate of change from n to n minus 1, now again, it's the other way around. So an individual of opinion 1 must change to opinion 0. How many individuals are there of opinion 1? N. Q1 is the probability that the individual decides to change its opinion. And this is the probability that in the binomial sampling, in the sampling, the binomial or sampling of 2k people, the number came to be k plus 1 or more. Okay. So this is the rate from going from n to n minus 1. And again, for the embedded Markov chain, we get that the probability of going from n to n plus 1 is again the rates divided by the sum of two rates. Earlier it was q0 over q0 plus 1, but now it is this complicated thing. And we call it gkn by n and gkn by n plus r, where gkx is actually this ratio, which which really gave us lots of trouble. This function gkx is 1 over x times the probability the binomial 2kx is bigger than k plus 1, or 1 over 1 minus x, that this binomial is bigger than k plus 1. So which we call gk of x, because it depends on k and the parameter x of the binomial. So in this case also, with probability 1, xn gets absorbed in one of the two states, 0 or 1, sorry, in finite time. And we are interested in the probability of absorption in the state n. That means state n means all n people have opinion 1, and the average time it takes for absorption. So as I told you, this gk was a nasty person function. So this function, this lemma really took us a long time. The gk is, this was the gk. So you should think of it as, let's say, p times probability binomial 2kp is bigger than or equal to k plus 1. And 1 over q, where p plus q is 1, 1 over q times probability binomial 2kq is bigger than k plus 1. Okay. And this function is strictly increasing, and therefore it's a one-to-one function. Once we have that, we get this theorem that the exit time is given by this nasty ratio. But more importantly, the exit time, when we start off with alpha proportion of people having opinion 1, this exit time, the probability that it goes to 1, in other words, all people's opinion all go to 1 as n goes to infinity, is only if alpha is bigger than beta. Otherwise, the society has an opinion 0 as n goes to infinity if alpha is less than beta. And again, this convergence is exponential in n. But what is surprising, this is really a surprising result, that it doesn't matter. Your alpha could be smaller than half. But if it's bigger than this quantity beta, then you still converge to the opinion 1. In other words, you can start off with a very small group of people having opinion 1, but being biased to their opinion, stronger than the other group with opinion 0. And as long as that is bigger than this quantity, gk inverse r, the small group of ones will dominate. Otherwise, it won't. So the proportion should not. So this in statistical physics, this is called phase transition. So this is the threshold beta, below which a certain regime occurs. In other words, everybody gets, the society gets absorbed to 0, and above which it all gets absorbed to 1. And because it is, this quantity is beta is this gk inverse of r, so you can solve for beta by Newton-Raphson method, the fixed point method or a Newton-Raphson method, by solving this equation, gk beta equals r. Okay. For the unbiased majority rule, we have r equal to 1, and gk inverse you can calculate is half in that case. And therefore beta is half. And that agrees with the known results, because in the unbiased case, if the proportion of people holding belief 1 is smaller than half, in the society all go to opinion 0, and if a proportion of people holding opinion 1 is bigger than half, then the entire society, as time goes to infinity, goes to opinion 1. Okay. And the mean time, remember, this is for the voter model, the mean time to reach consensus, starting with alpha fractions having opinion 1. So I'm saying consensus. The consensus could be at 0 or at 1. Okay. So for alpha between 0 and beta, then the consensus is at 0. That is, Tn alpha is again of the order of log n, and also for alpha bigger than beta. So the consensus time doesn't is of the order of log n, and it doesn't matter whether the consensus is at 1 or at 0. Okay. And for the proof of this, we need branching processes, and as I told you, that lemma 4, the monotonicity in lemma 4. So we can also derive the mean field limit in the majority rule. So I won't go much over that. So again, it's the same thing. Xn0 is binomial in alpha, and then Xn as a process converges to X, where X is a deterministic function whose initial condition is x0 equal to 0, and the ODE is given by h dot xt is q0 xt. So earlier, if you remember, there was a 1 minus xt times xt. But here now we don't have, we have xt times 1 minus xt and q0, but we have this additional terms in the product, gk xt, which I told earlier, minus r, and gk, and hk of xt, which is this binomial quantity. So basically what it says is that at time t, xt is the proportion of people with opinion 1. Okay, and 1 minus, so this is the binomial with parameter xt. Sorry, parameter 1 minus xt. Okay. And if you see, this term is just a binomial term. So it is always bigger than 0 for x in 0 and 1. And from this, using lemma 4, we can show that x dot has 3 equilibrium points, 0, 1, and beta. Okay. So 0 equilibrium points is the sense as where the consensus can take place. 0 we know, 1 we know, there's a beta which requires understanding. So beta is actually an unstable equilibrium point, in the sense that if you are at beta, you immediately move into either the region, the regime where the consensus is at 1, or the regime where the consensus is at 0. Okay, and that can be obtained by looking at when does the x dot t bigger than 0, and when it's less than 0. So now, I don't know how much time I have. Well, I have around 20 minutes. So what we'll do is, we have stubborn agents. What are stubborn agents? So these are agents who never change their opinions. Okay. So the clock can ring, but they don't care. They stick to their opinion. So we focus on the case when the updates occur according to the majority rule model. And the voter rule model with stubborn agents was studied earlier. And for that, one needed what's called a coalescing random walk. And this coalescing random walk doesn't apply to the majority rule model. But what we do is we study mean field techniques, because we know that the mean field techniques work for the biased majority rule. Okay. So let gamma I be the fraction of agents in the network who are stubborn. So I means at which opinion you are a person is stubborn. So gamma 0 is the proportion of agents who have opinion 0 and will always retain it. Gamma 1 are those who have opinion 1, will always retain their opinion. And so 1 minus gamma 0 minus gamma 1 is the fraction of non-stubborn agents in the network. And well, in whatever, in the Indian voting system, they are called the swing votes, right? Mm. The presence of the stubborn agents prevents the network from reaching a consensus state, because the consensus means the entire society has become one, or the entire society has become zero. But that can't be, because there are these fraction gamma 0 who will never be who will never change their opinion, and a fraction gamma 1 which will never change their opinion. So there was never a consensus state. Hmm. Yeah, so this is exactly what I defined here. However, the non-stubborn agent can interact and change its opinion. So the equilibrium fraction of the non-stubborn agents having opinion 1, that's what we characterize using the mean field techniques. And because using the mean field techniques, whatever we do for k equal to 1 will also hold for any k. So we just do it for k equal to 1. In other words, the individual samples 2 neighbors, including itself. XNT denotes, let XNT denote the fraction of non-stubborn agents having opinion 1. And again, Xn is a Markov chain which jumps at the Poisson when the Poisson clock rings, and it's only for themselves, because the stubborn agents we don't care. So this is the rate at which the Poisson clock rings for the non-stubborn agents. So what happens then? So suppose there are small x many, the proportion is small x of the number of 1 at time t, then it moves to x plus 1 over this, because this is the total number of non-stubborn agents. So it gets one more, the proportion becomes x plus 1 over this quantity, because remember, we are now looking at the proportion, not at the total number. Okay. And so we can also look at the transition rates of this process. So it goes, the fraction of people holding 1 goes from x to x plus this quantity. Is again a similar calculation. This is the total number of people who are in the population. 1 minus x. Let me just go back here. So, because this is the n times this is the rate at which the clock rings. Okay. And it samples 2. So if a person is 0, because this has to be 0 to 1, the person is 0, it has to sample 2 of opinion 1 from the entire network. And the probability that there are 2 of entire of opinion 1 from the entire network is exactly this product, because 1 minus gamma 0 minus gamma 1 x is the total number, the total number of the non-stubborn agents plus gamma 1 squares. So this is the rate at which it comes from here. And similarly, we can do the rate of 1 going to 0. And if we do this, then the mean field equation becomes this quantity. And we study the equilibrium distribution phi n of the process xn for large n via the equilibrium points of the mean field. From the ODE here, because there are squares here, xt squares and xt square here, so therefore this is a cubic the x dot is a cubic polynomial in xt. Hence, x can have at most 3 equilibrium points in 0, 1. And we can characterize the stability of these equilibrium points again by looking at the mean field theorem. By the mean field limit, the process x dot that we have has at least 1 equilibrium point in 0, 1, 0 to 1. Furthermore, the number of stable equilibrium points is either 2 or 1. So the third is not a stable equilibrium point. And if there exists only one equilibrium point, then the equilibrium point must be globally stable or attractive. In other words, it will always go to that equilibrium point. If there are two, then there's a probability of going to N1 or a probability of going to the other. And in this theorem, we give conditions on the, remember, gamma 0 and gamma 1 are the proportion of people, stubborn people with opinion 0 and proportion of stubborn people with opinion 1. So based on a relation between these two, which involves all kinds of things, we can get that if any one of the above three conditions, I'm not going through this because I don't have much time, and also these are the notes will be available on the web also. If any of the above equilibrium points, above conditions are not satisfied, then X hat has a unique globally stable equilibrium point. So we can characterize when it has only one stable equilibrium point or only two stable equilibrium points. So, and so characterize because of this if and only if statement. Also, any limit point, as I told you, when it doesn't have any, when it has exactly two stable equilibrium points, then we have to find out the probability that it goes to 0 or 1. And when it doesn't have, of course, we don't have to put that probability because it goes to only that quantity. So what we know is that the any limit point of this sequence pi n, which is the where was it? Where did I write? Well, pi n was the stationary distribution when there are n agents. So pi n is the limit point of these pi n's is a convex combination of the Dirac measures. Dirac measures are measures which are concentrated at single points and concentrated at the equilibrium points of these two. So in other words, if there are two equilibrium points, then pi n would be some alpha times the Dirac measure at 0 and 1 minus alpha times the Dirac measure at 1. Where alpha and 1 minus alpha are of course not related to the original thing. So let me call it gamma and 1 minus gamma. Okay. So the limit measure will give me the probability of getting consensus at 0 or the consensus at 1, these two equilibrium points. And in particular, if there's only one equilibrium point, we can find that out from this theorem, whether there are 1 or 2. And if there's only one equilibrium point, then the Dirac measure is concentrated at that point R, where R is the equilibrium point. So we did some simulations, and we did some simulations, and that just tells us what to expect. So if you want to look at the equilibrium point of the mean field, then when the proportion is, let's say, gamma 0 is 0.27, and here is the proportion of, let's say, the proportion of stubborn gamma 1 is at 0.2, then the equilibrium point is here around 1 point something. Okay. Similarly, for different values of gamma 0, and this is the scale of gamma 1. And we choose the parameter value so that there exists a unique equilibrium point. Otherwise, it doesn't make sense because we're looking at only unique equilibrium point, and that we can choose because of a theorem, which in our paper was called proposition, but for some reason I call it a theorem. And to demonstrate metastability, so we simulate a network with n agents, gamma 0 and gamma 1, the proportion of of them stubborn at 0 or stubborn at 1, both being 0.2. When the mean field has two stable equilibriums, one near 0, which is at 0.12, and the other is near 1, which is at 0.18. 0.88. These two add up to 1 by 2. And we showed this here. So what happens is basically you can start with whatever fraction, and then it just comes quickly and goes near 0. So the non-stubborn agents are very close to 0, but they're still sampling. So after after a rare thing, one of them or a few of them suddenly moves to 1, and then it slowly drags everybody. And this oscillation just goes on. So to finish with, let me do, so we looked at the complete graph, right? Now let us look at a deregular random graph. So deregular random graph means it's a graph where each vertex has exactly, it has degree exactly 3. So there are exactly 3 neighbors of any vertex, exactly 3. So that's called a deregular, and one can do it one can construct it in a random way. So so you start with a vertex 1, and you first choose 3 at random. Then we do a 2, and if 1 is connected to 2, then of course it has to choose only 2. Otherwise, it chooses 3 at random. In this way, we can actually construct a deregular graph. And for fixed D, the neighborhood size of each, as we said, of each agent remains constant with respect to n, as opposed to earlier. And here also we note that the time of the consensus is of the order of sorry, this is not the time. This is in the earlier case, we said that we could sample from n over 2 or any n of this agent, but we could have also restricted ourselves to any number which is of the order of n. Here again, this doesn't grow in the order of n. Okay. But here also we observe that the mean consensus time is of the order of log n. Okay, when the agents are biased, as opposed to theta n when of the order of n when they're unbiased case. And this is exactly what the mean consensus time is saying, that in the biased case it grows logarithmic, in the other case it grows more or less linear. The exit probabilities also we can see, in one case it's the biased case it goes to 1 exponentially. In the other case, it goes linearly. So this is for the majority rule. In the majority rule, we just sample, any individual just samples 2 of its 3 neighbors, because remember, any individual has only 3 neighbors, samples only 2 out of the 3, and then decides to change or not change. And we get exactly this very similar results as our earlier thing. And well, we haven't really worked on it, but I think the calculations can be done based on what we had done for our earlier work. So that's really my talk, and as I think the link is already given on the web page of the webinar. And then thank you. And I just have to quote with a statement from Ambrose Bierce from 1906, the Devil's Dictionary, to see how idiotic I am. To talk is to commit an indiscretion without temptation, from an impulse without purpose. It's a transition. Thank you.
Thanks a lot, Rahulda. It was a really fantastic talk. So, Digantada, over to you.
Okay, so I have not seen any questions in the chat. So to all the attendees, if there are questions, now you are free to unmute your microphone and ask questions to Professor Roy.
So I will start with a question.
Sure.
Okay.
Let me inaugurate. Rahul, so the in the last part of the talk where you were talking about the not the random graph, not the complete graph.
The regular graph,
Yeah. So in that scenario, I just want to know, just to have an idea, that if the agents, so agents are sampling from the neighborhood, right?
Right.
So agents are basically observing agents who are in their neighborhood.
Right.
So in case where the agents can observe not only the neighborhood, but also other clusters. So agents, let's say neighborhoods are also neighbors to each other, right?
Right.
Uh, so if I am in my neighborhood and I can observe what is happening in the next neighborhood, let's say I'm in ward number 14, I can observe what's happening in ward number 15 or ward number 16. So in that case, can the alpha be even more smaller for the quicker, convergence? Because then then basically a small number of neighborhood has to convert, and that will give essentially a perception of the global, which is not true. It's the perception of the local which will make the convergence. Is it true?
See, no, but okay. So I have, let's say, 3 neighbors, right?
Yeah.
But my neighbor A has 2 other neighbors. So what you're saying is that if I can observe through my neighbor A what A1 and A2, his or her other neighbors, if I can observe that, right? But I mean, these 2 other neighbors are also affecting A. So when I observe A, some part of that is already included, how A1 and A2 are influencing A. But yeah, you're correct. But the correlation between me and somebody who is, let's say, if I call it key hop away. Key hop means I go from me to my neighbor,
Yeah.
and etc. The correlation between me and the key hop is actually very small.
So that really doesn't affect the convergence time much.
Yeah, the convergence time is again this log n, but what it can affect, which is which we haven't done, that alpha and beta, which you're talking about.
Yeah.
The phase transition point beta, the threshold, that will be different, and that I think will depend on how many. What is my, so in this D regular graph, that will depend on D. And it will come through, the correlation will basically come through this D. So clearly, if I have a large circle of friends, then I don't need to go key hops. Then I can go much faster.
Right.
So
that is those influencer model kind of that.
Right.
So
Right.
Okay. Yeah. So that's what I wanted to understand. Anyone else, please ask your question, whatever.
I had a comment or suggestion to make. The relation here that between dynamic opinion formation and a Markov process that's really basically a lot like a random walk on a lattice suggests to me a possibly interesting extension to this work, to the dynamics with respect to an M vector of opinions. And I think that for small m, you could still get results with regard to consensus formation over time. But based on long known results on random walks, on ordinary random walks on lattice in various dimensions, I conjecture that, that the nature of the results that you would get would change drastically when you went from m equals 2 to m equals 3 or above.
Yeah, I mean, I would guess so also. M equals 3 above would also be, there'd be a significant change. Yes, but yeah, you're correct. Yeah. But that in some sense would be like, if you are having a random walk, again, since you're bringing in random walk, there are also, of course, there are questions of random walk and branching processes, which we need in this thing. that would be like having a random walk on a triangular lattice. So, so if you are closer to, let's say, let's look at an equilateral triangle and the triangular lattice there. So if you're closer to, let's say, the left side of the triangle, that means you're closer to an opinion 0, opinion 1, or an opinion 2, and the other 3. So I would guess one can still formulate it as a random walk, but you're correct, that the results would be significantly different. But this is just this is just speaking out loudly without any reason to believe that the equilateral triangle model can say something.
Well, actually, I was thinking more of opinions on M different topics, like I don't know, abortion, climate change, homosexuality, etc. And that's what I was thinking would give you the multidimensional lattice. But
right, no, here, for example, when I'm talking about consensus at 0 or 1, so I'm really looking at a linear case, right? So 0, and so now I want to look at, let's say, 3 different opinions: homosexuality, racism, and whom you vote for. Okay, so I can say that, okay, if the population is closer to this side of the equilateral triangle, then it is more closer to racism. Oh, well, but what is the other side? Yeah, you're correct. You're correct. So yeah, so the equilateral triangle wouldn't give anything. Yeah, I understand. Right. So you may not have any random formulation. Yeah, thanks for asking. That's a nice, very good question if you think about it.
Yes, anyone else?
Hello, this is Kavita.
Yes,
Hi, Kavita.
Hi. So actually the talk is nice, and I was just wondering, like, if we move from D regular graphs towards the complete graph, how does it look? Any idea? Like,
No idea. No idea. So this is exactly what Anirban was asking. In some sense, it's connected. So what we really want to know is
yeah,
the
he was asking about,
correlation between one individual and the other who is at a distance k away from you.
correct. He was saying that, but I was just wondering if we increase the number of neighbors.
Right.
So it will not be hop, but they will be neighbors now.
Right.
So is it that we reach the consensus faster?
No, I think the time for consensus in this case also empirically looks like log n. But so it's just the constants which would, I guess, change and nothing else.
Yes.
Yeah. So in the sense of order, it will still remain the same, I would guess. Yeah, but as I told you earlier, that the phase transition point beta, that I think will change dramatically. So probably, it will be a beta D, which goes to the beta of the complete graph as D goes to N.
Yeah. But I was just thinking, yeah, I understand what you're saying, but yeah, is it only log? I mean, if you have more neighbors or more, I mean, if you go to the complete graph.
No, so as you see,
So
your certain
maybe,
mean consensus time is theta log n.
yeah. No, I'm just thinking, like, if I, let's say, are you also scaling K if it is in majority voting with N?
So in the complete graph case, it really, you don't really need to look at a complete graph. If you have neighbors, the number of neighbors is of the order of n. So if you have if you have, let's say, n by 2 a deregular graph, you get the same result. So if d is n by 2, you get the same results as we had earlier, because you're sampling an order of the entire population. That's enough. But what I think is the in that complete graph case, if you sample, let's say, n to the square root of n, then we don't know what happens.
Huh. So I was just telling that K, capital K, which was the number of people that you're sampling in majority voting.
Right.
That we
Yeah, so that is the result. That's the reason why we looked at the d-regular graphs, because, as both of you commented, as d goes to n, we should recover all our earlier results, right?
Huh.
And because our earlier results really needed that you have your neighborhood sizes of the order of n. If you are more of a loner, you have very few friends, then what will happen, right? And I mean, I think that as d goes to n, the results should corroborate the other case also, but I don't know anything more than that.
Thank you, Kavita.
Are there any other questions or reaction, comments?
Good, I'm far away. If there's violent reaction, I'll be saved for it.
Okay, so if there are no other questions or comments or reactions, benign or violent, then we should probably thank Professor Rahul Rai once again for a very interesting talk, and with stubborn agents at that. So thank you, Rahul, and I hope you have also enjoyed being with us.
Yes, thank you very much.
He will be with us in future also.
Sure. Thank you.
Thank you so much.
Thank you.
Thank you so much. And we will meet soon again. So in another 2 weeks, we will have George Zakur joining us. So I will send the invitation in due time. So thank you all. Thank you for being here. Thank you, Rahulda. So we'll end the